Welcome to lecture number 12. You recall that we've been working in the Lorentz gauge given by divergence A plus 1 over c squared del V by del T. We have written the factor here as 1 over c squared by using the fact that the reciprocal C is nothing but the square root of the product of the free space permittivity and permeability. In the Lorentz gauge, the potentials V and A satisfied similar looking expression. So it suffices to just consider one of them. Let's say consider V. And in terms of V and A, of course, we can we'll be able to calculate the corresponding electric field E and magnetic field B. Now we noticed that V is linearly proportional to rho, so that thus prompts us to write V as integral involving rho, linear, so that V would be linearly related to rho. You'd increase rho twice, V would increase twice, etc. So that what connects rho and V connects the source, and what's observed is this function G, which depends upon the location and the time of the emission, and the location and time of the observation. So the G has the meaning of some kind of propagator. So that's this type of source propagate to the observation point. So that obviously a physical thing to do is to make sure that the observed time is after the emission time. Since it takes the signal finite amount of time to get from the source R prime to the observation point R. And that since V has to obey this four-dimensional differential equation, that means that the four-dimensional Green's function has to obey this relation. And last time we spent most of last lecture in solving for the Green's function. And the result is surprisingly simple. Namely that we found two solutions. One is this one is equal to 1 over R minus R prime times this delta function. This delta function says that T has to be equal to T prime plus the amount of time that it takes light to travel from R prime to R. So that this solution of Green's function is consistent with our idea of causality, namely that always cause effect after the cause before the effect. You also remember that, in fact, and we call this kind of this solution corresponding to the plus sign here to be the so-called retarded Green's function. And there is another solution which in the literature is known as advanced Green's function, and that corresponds here to be minus. But for this solution, then what you find is that the emission time would be after the observation time. So that is not consistent with our idea of causality. So that we will drop this advanced Green's function and use this retarded Green's function. So that the retarded Green's function is equal to 1 over R minus R prime, which, by the way, is the solution for the three-dimensional Green's function. Not a four-dimensional Green's function. That's an extra factor of delta function. So that, and let me, as usual, write R minus R prime magnitude to be this R. So I have delta function of T. Let me rewrite this. T prime plus R over C minus T. That is the solution for the Green's function that we need. And now we can plug this solution for the four-dimensional Green's function into this integral equation to get the potentials. Here, V, of course, that involves, let me put epsilon dot here. Whoop. Yes. Where's my, here. Of course, you can solve for the vector potential in a similar manner. All you have to do is to replace rho divided by epsilon naught by mu naught times the current density, the R point, T point. And, before I proceed to work things out, let me tell you a story about George Green, who was the one who first found solution to the Green's function, who introduced the Green's function on the name after him, of course. And now, as I told you last time, in 1993, on the year of the bicentennial year of George Green, Julian Schwinger, my late thesis advisor, was, among others, he was invited to attend a symposium in honor of George Green in Nottingham, George Green's University. And as I told you, Julian Schwinger gave a talk, and the title was interesting. And it was the greening of quantum field theory, George and I. So in that talk, he traced the history of Green's function, development of Green's function, and his career as a physicist in applied Green's function techniques to quantum field theory and to quantum electrodynamics theory, etc. And so George Green introduced this technique almost 200 years ago. And he would be really greatly baffled that we are still talking about the functions that he introduced almost 200 years ago. So at the end of Schwinger's talk, Schwinger said the following: "So ends our rapid journey through 200 years. What, finally, shall we say about George Green? Why, that he is, in a manner of speaking, alive, well, and living among us. It's amazing that we are still using his techniques he introduced almost 200 years ago. And now let me tell you a story about George Green. It turns out that George Green, in contrast to what you might think, was by no means a prodigy. In fact, he was slow. He did his work on the Green's function at a relatively mature age. Let's put it that way. Actually, it was up to the old age. And this fact was alluded to by Schwinger at the very beginning of his talk. Schwinger said, "The young theoretical physicists of a generation or two earlier subscribed to the belief that if you haven't done something important by age 30, you never will. Obviously, they were unfamiliar with the history of George Green, the miller of Nottingham." As I said, George Green did his important work at a rather old age. So the lesson is that if you have not done anything important early in your career, don't give up. Don't feel despair. Keep on working hard. And you will have a chance to do something great, like George Green, whose work is still being used 200 years after he introduced that technique. To me, I feel uneasy about the way that research is being conducted, at least in academics. Nowadays, okay, researchers tend to write many papers, and they just follow each other. Okay, putting in no new techniques, no new ideas, no new concepts. I can understand why they're doing that. That, I think, is partly because of the fact that if you do not publish enough papers, okay, you will not get grant to do your research, and you will not get promoted, okay, and you, okay, in universities, you will not get tenure, and it's important to get tenure. I agree with that. But okay, unfortunately, okay, the tenure system has the tendency of putting pressure on young faculty members to work on, I wouldn't say, well, to work on problems which, okay, are easy, relatively speaking, so that they could get results easily, but not important. Well, of course, okay, if you go into academics, you have to get, you really want to get tenure so that you have the freedom later on in your career to do things that you're really interested in. Okay, those things that might take a lot of time. Okay, that you cannot afford if you, okay, do not get tenure first. I understand that. But I do hope that you will remember the story of George Green, who, okay, did his important piece of work, okay, at a relatively late age in his life. Always, okay, remember, try to work on something important if you can afford it, okay, and keep on trying, keep working hard. Okay, with that, okay, let me go back to history, to physics. All right, so then now, okay, we have, okay, the Green's function given here. Okay, now we can plug that in to give us the potentials. So it's given by 1 over r minus r prime. Then the delta function of t prime, okay, minus t, let's see, t prime is minus t plus, okay, r minus r prime over c. So obviously, with the help of this delta function, you can do the integration over t prime right away. So, okay. And now I'm done with all this. So may I, okay, erase this? So that, okay, v of r, okay, t is equal to 1 over 4 pi y integral of, okay, this is the 1 over r minus r prime, okay, times rho divided by epsilon naught at r prime, and t prime now is given by t minus r minus r prime over c. So the time dependence, okay, now appears as this combination of the time observation, okay, and this amount of time that, okay, the signal travels from the r prime to r. And since this appears so often, okay, and since we have used the retarded Green's function to arrive at this result, okay, this time is sometimes written as t sub r, the retarded time. T minus r over c. And similarly, of course, okay, A will be given by the same thing, except that, okay, the source would be just the mu naught instead of 1 over epsilon naught, and the current density, okay, at location R prime and at the retarded time. Now, okay, if it, okay, don't look at the time dependence in the source. Just this. Okay. You will be seeing something very familiar. Now, this will be the result, okay, for the static case. So it's amazing that, okay, what we have found is, okay, just the static solution with, okay, the time dependence on the source being the retarded time, which reflects the finite speed of propagation of light. And that's all. So that we can now, okay, use all our solutions in the static case, okay, and promote it to be, okay, the case that we're talking about by replacing, okay, the time of emission, the T prime. Okay. I hesitate to call time emission at this one, okay, because I'm going to, okay, I'll come to, in fact, in addition to introducing this T sub R, I will introduce another time, which approximately equal to TR. Okay. And I call that emission time. So that's why I hesitate to call that this emission time at this point. All right, so let us, okay, give an example. Let's say that we have, okay, an infinite long straight wire, and the current is supposed to be straight. And the current was switched on at time equals 0. So the current Ti, okay, is equal to 0 before time 0, and it's a finite amount, T naught, okay, for T after 0. And we're supposed to, okay, flowing in this direction, okay, and we're supposed to, okay, find, okay, the magnetic field B and the electric field E outside of this Y. Well, if we, okay, of course, okay, if the current, okay, is, okay, I naught independent of time, then that's the static problem, and we know the solution already. Static case. Okay. Okay. I'm sorry. Presumably, okay, this Y is neutral. Okay, so they, okay, so that V is 0. Neutral. Potential 0. Okay, now let's okay, think about the static case that there's a current I not go through this infinite long Y. And let me take this to be, okay, the Z-axis. So unit vectors are non K. So that we see right away that, okay, the vector potential will be given by, let's see, mu naught over 4 pi, okay, I naught, I, okay, which is in the K direction, okay, divided by, okay, R minus R prime, integrate over the whole, okay, it's along the Y from minus infinity to infinity. This is A at, say, location R at this point, which is, okay, distance R from the Y. Now, okay, from this static solution, we can now go to, okay, this problem, okay, namely that, okay, current is given by this. All right? So that now we have A and R T would be equal to mu naught over 4 pi, integration over z from minus infinity to infinity. Now, with the t now in the source being the retarded time divided by r. That's the only change the derivative will make. But it's a crucial change, as I will show you. All right. So let's see. So that I can erase this. Okay, more space here. Okay. Oh, I have a lot more space here. All right. So continue. So let me draw the straight line again. So I'm interested in this. So let's take this to be the origin of the coordinate system, and we're interested in calculating the vector potential at this point, which is r away from the straight y. All right. So now we have in integrand we have to use the current at the retarded time, which of course is 0 for TR, less than or equal to 0, and I naught for TR greater than 0. All right. So let me draw. So let me draw the diagram at time t. First of all, if there's a current I at this point, then it would the signal will have to travel this distance to the point of observation. So the time will be R over C. So that for t before R over C, the fact that there is a current flowing on this y is unknown to the observer at this point. So that A would be 0. So let's talk about time. After this R over C. So let us draw 3 lines. So you look at this. Oh. Let's call this distance to be CT. So that this distance is CT, and that corresponds to TR being 0. Because TR, remember, is this TR is nothing but T minus R over C. And since this R is CT, so it will be T minus C. So that this path corresponds to TR equals 0. And let me draw so that any other path above this connecting a point on the z-axis and this point of observation. Let me use green. Obviously, this R for the green is greater than this one. So that this path will correspond to TR less than 0. And let me plot another path below the red one, which is the critical line. So this one. Okay, so let me call this point, okay, to be coordinate z. So that this r is given by square root of z squared plus r squared. And let me call the length element this to be dz. So all we have to do is to do the integration. Okay, over z from well, from this point origin up to this point, because information about the fact that this current above this point at time t is not known to the observer at this point. So that we have the result. For the calculation is simple. All we have to do is to integrate over z. Of course, this is symmetrical up and down, so that we have to include the contribution coming y below this, so that would give me a factor of 2. If I start the integration from z of 0 up to this point, z x 0, and up to this point, what's this? This is nothing but square root of ct squared minus r squared. Square root of ct squared minus r squared. And this is and the current, the value for current is I naught, so can be pulled outside. And this r is, of course, this r is given by square root of z squared plus r squared. That's it. And so exercise. Find the, do the calculation, do the integration. And once you have done the integration, then obviously you can find the field, the electric field E and the magnetic field B. So electric field E, continue here, is given by, remember, minus gradient electron V, but V is 0. So the only contribution to this would be minus del A by del T. A is found to be this result, so you can get this. The integration is slightly complicated. You can look up the log table, integration table. And then for B, B is nothing but a curve A. Since curve of A, and since A is in the z direction, so this depends upon z. Obviously, the only contribution you will find is doing something along the azimuth angle. Exercise. Find this also. But of course, whenever possible, you should check to make sure that your solution makes physical sense. So one check for this problem is to consider time goes to infinity, so that they would become the static case again, and you know the static case solutions. So check is consistent with with the static case solution. All right. So now, okay, now that we have, okay, let's see. So let me, it's important for me to keep this here. And I can now erase this. And this I have to keep. And this, okay, I erase. We know the solution already. So this. All right. Now let's take a look, okay, at the time dependence for rho and j. And okay, erase this. I'm done with the example. Time dependence. The time dependence, of course, is given by the retarded time, which is the time of emission, being related to the time of observation, minus the time that it takes to travel, for light signal to travel. This is R. The very fact that the time of emission, given by retarded time, is not the same as the time of observation. As you will see, it's a cause for the existence of this. That's what gives rise to electromagnetic radiation. And thank God for that, that this is not T. All right. Dependence of time. It's given by the retarded time, T. Use small is equal to T minus R minus R prime over C. R prime, of course, refers to the coordinate of the sources. So let's say that the source is confined within a certain region, and the coordinates being given by R prime. But let's ask for the field and the potentials at a point far, far away from the source. It is with R. Then obviously it makes sense to take expansion for the R minus R prime. So let's do that. R minus R prime magnitude. That of course is nothing but square root of R minus R prime square. And it's equal to square root of R square minus 2R dot R prime plus R prime square. Square root. Since I'm very interested in R, much greater than R prime, we can now, as first approximation, ignore this term. And then make a tail expansion for the square root of R squared minus this. So what's that? So let me pull out this square root, this R squared, and this square root, so this R outside. This will be 1 minus 2R dot R prime over R squared. 1/2 power. And tail expansion for square root of 1 minus something small compared to 1, of course, is nothing but 1 minus 1/2 of this, which is 1/2 cancel out 2. R dot R prime over R squared. So the result is R minus this 1 part of R, so that I have R, yes, right. R, so I have here R vector divided by one of the square will cancel, one of the part of R cancel with this R. So that I will have R over the magnitude R. that of course is nothing but the unit R vector, okay, pointed to the direction of observation. All right, so that I have here R minus so R dot R prime. Have I made any mistake? I think I am right. So that with this approximation, I can write the retarded time as T minus R over C. And then with a little correction coming from this one, minus minus is plus R hat dot R prime over C. And later on, just for your information, I'm not going to use this yet. Later on, we will drop this term and approximate the retarded time by just T minus RC, and I will call this T sub E stands for time of emission. But I'm not going to do it now. So, but just for the information, I will. So you will know that TE is almost equal to retarded time after this point. So let's not do it at this point. And also for your information, this correction term would be kept for only in two important places, and I will tell you where later. All right, so continue. So the retarded time can be now replaced by this. So from now on, in fact, I will call this to be my retarded time, even though that was, in fact, only an approximation of retarded time. But from now on, I will call this combination of T and R prime to be retarded time. So all we have to do is replace this T dependence in the source by retarded time. With retarded time being approximately equal to T minus R over C plus R hat dot R prime over C. Okay? And now, once we have the potentials given in terms of the sources, we can now work out E and B. And in E, there are two terms. This involves del by del T term, and I will leave this alone for a moment. And let me concentrate on this term in E, involving gradient acting on V. And also, of course, I will also talk about B, which involves the gradient of its curve A. So let me take a look at this and this. With V and A given here already. So that I'm interested in gradient acting on this. And I can use this. I can use this, not this. So I have gradient. But this eventually will turn into gradient. This is cross. So we're talking about curve. But the important thing is that this involves the gradient operator in both places. So let me not put in the cross at this point. So the gradient acts on things depending on R. R appears here, and appears here, and also here, actually, in the time dependence argument. So that I'm interested in gradient acting on this, and I will here that's approximated by 1 over r. Dropping r prime completely. Okay, you said, wait a minute, but okay, in the return time, okay, you did keep this term, right? Yes. Okay. You can, in principle, always keep that dependence on that little correction here. But it turns out that to the approximation that we will be making, it's no need. Believe me. You can check for yourself later on. So the drop r prime completely in this 1 over r. Okay. And here, we would replace the retarded time by this combination. So that I'm interested in gradient acting on 1 over r times something, either rho, or which is a scalar, or j, which is a vector. But let me call this f. F can stand for either rho or j. And let me suppress the r prime dependence. It plays no role in this argument. So let me just write down the time dependence, which is tr. So this tr is now approximated to be t minus r over c plus r hat dot r prime over c. So let me consider this. With gradient being operated acting on 1 over r as well as on this function. Gradient acts on this function because the time dependence involve r and this r. All right? So first of all, let me act on this. Gradient acts on 1 over r. Of course, that will give us 1 over r squared. Then I have gradient acts on r. Then of course, it's nothing but the unit vector along r. So there's r vector. Times f. Now the complicated thing is that in the time dependence of the sources, there's this dependence on r and this on. It turns out that I can in fact drop this term to the order of approximation that I'll be making. So forget about this. Then now, gradient acting on this, leaving me this alone. So there's the plus 1 over r factor. Then I'm gradient acting on this. Well, this r dependence appears in the time dependence. So how do we do it? All we have to do is to use chain rule. So that this acting on that will appear as del f by del t, and then gradient acting on t, this t, pr, and del f by del t, of course, eventually evaluated at tr, the retarded time. All right. So the question is, what is this? When gradient acts on this time dependence. Let me do this here. Gradient acting on t minus r over c plus this small. No contribution come over here. But when it acts on this one, it's equal to minus unit vector over c plus corrections, which I wrote down in my lecture notes. But in fact we do not have to keep it. So let me in fact forget about this. So that this gradient acting upon TL is minus r hat over c. I dropped this term. But this term is of order 1 over r as far as the distance is concerned. Whereas this term falls off much faster, because it's 1 over r squared. So that in fact, I can drop this. That is also the reason why I dropped okay, R prime dependence in this, 1 over R factor. All right? So that, okay, all I have to do is now, okay, replace, okay, write okay, the gradient acting on 1 over R F of TR is approximately E given by minus okay, R hat over C and over R, then del F by del T, evaluated at the retarded time. Great. Next. Oh, I can use this as a blackboard. I'm done with this, so that I can erase this. All right? So we have considered this gradient acting on this. And as I said, this F okay, could be rho or could be J. Okay. So let me okay, apply this to, okay, to the expression for B first, which involves, okay, so if F were J, which is a vector, J, F is J, then also remember that it is the curve that, so I'll just put back that cos, so that this will be involve okay, curve of J, and here, okay, that will involve R cross this, del J by del T. All right? So let me do that first. Okay, and get the expression for B. So B at the location R at the time T will be equal to, okay, gradient on that one. So A is 1 over 4 pi, and this dependence on mu naught upstairs. All right, and then what do I have? I have now, this is my J here, so that I have 1 over R, can we pull outside? Integral 1 over R, and then there's 1 over C. I've done this, okay, and then I have, okay, R hat cross, okay, what if I have this one? Okay, so this is 1 over R, is taken out already. Oop. Oh, yeah, I've done this already. Okay, this R, 1 over R is here. So that's taken care of. And then I have integration. Okay. Let me go back to the notation. D tau prime is dr prime. And minus that, and then I will have 1 over R is there, then R hat cross it. What I have is, okay, here inside is del by del T, acting on F is now J, at okay, R point location, and okay, the retarded time T, evaluated at okay, T is T point. So that would be, okay, the cross here stands for the cross product between R hat and J. All right. Next, let me check with my notes to make sure that I've not missed any factors, which I have the tendency of doing, unfortunately. So that, let me check. minus sign. Yes, see? Minus. Minus. Minus mu over 4 pi 1 over r hat c cos. Correct. Next, okay, let me write down E down T. Consists of two terms. Okay, this term, okay, is minus del by del t epsilon A, and A is here. Okay, so del by del t x on, okay, this. So that, okay, I have for A, okay, 1 over 4 pi. Okay, there's the 1 over r. And then the rest, and then there's the mu naught. And then I have the del by del t acting on j. And this minus sign is put up there already. So del by del t acting on j. That's S, okay, the expression for B. Involve del by del t acting on j. Oh, okay, I forgot about the volume integral. Okay, we have the volume integral. Volume integral. Acting j r prime t inverted at the total time. Now, I have this term, gradient acting on v. So the gradient acting on v, so f is now my v, a scalar. Oh. And there's no cross, unlike in the cross for b. And then my j, my f, is j. Okay, so that additional term for E would be minus 1 over 4 pi. Okay, and then the volume integral. There's a 1 over r factor can be taken outside. What else? Then now there is, okay, R over C, oh, that's a minus is plus. Sorry, plus. Okay. Let's see. This A, so that's mu naught. That's mu naught. Oh, I'm sorry. I'm looking at gradient acting on V. Oh, gosh. And in V, there's the epsilon naught downstairs. And then I have, 1 over C. Then, let me, so I have, need some more space here. Integrate OT tau prime. I have, R hat over C. Come from here. And then I have del by del. Oh, sorry. So this one is, first term is del by del A, so that derivative of J, this now I have this gradient acting on V, this one, okay, and so that I will have, oh, okay, so I have del rho by del T, good, scared me for a moment, okay, so I have taken care of R over C here already, there's R already here, then I have epsilon naught there already, so I will have, okay, 1 integral of del by del T acting on rho, oh, good. And rho and R prime T prime. Okay. Take derivative at T equals TR. I think that's all. And okay, let me check against my notes because I've been making mistakes. What's this? Okay, so E to B is checked to be correct. So A, okay, this I have checked to be correct. So second term is R hat over 4 pi epsilon naught, 1 over R. That's a C, 1 integral of this. Correct. Now, notice in B, in integrand for B, okay, you have del J by del T. And the first term E also involves del J by del T. But the second term is del rho by del T. So, okay, we have to do something about this. Is it possible to convert this del rho by del T to del J by del T so that okay, all three terms will have the same structure involving del J by del T? And the answer turns out to be, oh, wow. Simon. Okay, we have to hurry up a little bit. Okay, it turns out to be yes. If we use the local conservation of charge. So we are interested in, okay, psi calculation. So we're interested in del by del T acting on rho of R prime T. Okay, if we have understood to be at time, which of course has dependence. T prime is retarded time given here. Okay, is R prime dependent on time is okay, T minus R over C plus R hat dot R prime over C. This. And of course, we said that, okay, so this is what I want to calculate. But conservation of charge says that this is nothing but minus the divergence of J at R prime. So divergence prime dot J at R prime, then the retarded time, T minus R over C plus R hat dot R prime over C. Correct? So this is okay, the expression for conservation of charge. Not quite. It is here, this is the first place where we have to keep this term for consistency. Okay? So there will be another place where I will keep this. Okay? But that will be later. By this point, okay, we have to keep this term. Why do we have to keep this term? We have to keep this term in the time dependence because it depends on R prime. No, that's R prime. So that when we make use of conservation charge, we said del rho by del T is divergence J. We assuming that in fact there's no R prime dependence in the time argument, but now there is. So this gradient, this grad prime acts on R prime in J. It also acts on this in J. Okay, but conservation charge only says that this divergence only acts on this R prime. Okay, the position dependence, not on the time dependence. but there is. So we have done too much derivative gradient operator. So we have to subtract it off. Minus is plus. So that we have, how do we take this x on that? Of course, this again is depends. This term depends on the time dependence of j. So again, we use chain rule. So del j by del t of r prime return time evaluated at return time, and then we have there's the dot here. Then we need gradient prime x on this. X on this, and the only place where r prime appears is this term. So r hat dot r prime for c. That is. So that this will just give me r hat over c. All right. So in place of this del rho by del t in this term in E, I can replace it by minus divergence of j, and then this term, namely that I have plus r hat dot c dot, that's this dot, of del j by del t. So that at least this term with the structures that we want involving del j by del t, del j by del t. Good. But what about this term is that? Don't worry, it's zero upon integration. D tau integration for divergence of j. Of course, can be converted into a surface term, but since j, the current, we assume to be bounded, so on the boundary it falls off to zero. So this is zero. So there's no contribution come from this term. So then now, with this little exercise, I can replace this by that. So let me so this is that, equal that. And before I let me check to make sure that I have not dropped anything. So I have R, then R have got that. Okay. So let me recopy this maybe, just in case I made a mistake. And so let me erase this. I'm done with the side calculation. So that, so this term would be, so E is given by this term plus this term. And this term now, let me write down this green color. So this term becomes 1 over 4 pi, 1 over epsilon naught, 1, and there's a C, 1 over R hat. Then I have R hat dot C, over C dot 1 integral of del J by del T evaluated at T equals TR. So next now, as I said, this simple exercise allows us to, where is my green? Oh gosh. Oh, okay, I have one here in my pocket. So notice, So we have this, and now this term is also the same structure. That. So they all have the same structure. Good. Involving the volume integral of the time derivative of the current density. All right. But okay, the expression over E is complicated, involving two terms. It would be nice if we can combine them. After all, both of them involve volume integral of del J by del T. Okay, and so let's combine them. It can be combined in the very nice form. First of all, we notice that in B is mu naught appears, but here for the second term is 1 over epsilon naught that appears. So we want to change this dependence on epsilon naught to mu naught. How do we do that? This is easy. If we multiply upstairs and downstairs by mu naught. And you remember the product of epsilon naught and mu naught is nothing but the reciprocal of c squared. Is the reciprocal of c squared. Okay, so the 1 of the c cancels. So that upstairs and this. Let's see. This mu 1 of c squared, the c cancels. So that's mu naught. Oh, this mu naught, that's correct. It's clear for me. All right, so this c cancels this c. So that, in fact, I can now erase the thing and change this. Correct, right? Well, I have my notes so that I can always make changes later. So that this term involves mu naught, so it's this one, and mu naught. Good. Now I can combine this. All right. Notice that these two terms are very similar, except that in this term, it involves instead of just this, involves r hat, r dot this. So let's combine them. Let me call this it's a vector. So let me call this vector v. And I can always decompose v into a component which is perpendicular to r hat and a component parallel to r hat. What I mean is that I can consider, let me do here. So let me consider r hat cross r hat cross this vector v. And this is equal to the triple cross product. So there are two terms. One is in this direction, r hat times r hat. This r dot v. This is the term. This is in the direction of r. Then minus v. Minus v. R times r is r times r hat times r is 1. So that I can write v as, goes to the other side, as r hat dot v minus r. So minus r hat cross r hat cross v. So the v minus this is that. Lo and behold, if this is a v, you can check. This is that term with a relative minus sign. So we identify this. See this r hat over r hat dot. This was v. So this we identify as this term minus r hat times r hat dot v. If this thing is v. So the result is this. So that the two terms combined for E to give me this result. Let me, where do I want this? Okay. Okay, this is my V. So let me, okay. I hate to erase this, but I have to, I need space. I hope I haven't made a mistake, otherwise I will not be able to see what I started with. So this two terms combined to be V times, now there's a minus sign. There's a minus sign of r hat cross r hat cross this. Where's C? This is C somewhere. I must have, by mistake, erased it. Oh, no, this E, that's right, sorry. No, you got it yourself, sorry. E has a dimension of B times C. The C cancels the C, no mistake, that's okay. Okay, so this is equal to, notice that we have, what we have here is, so the minus r hat cross, this. Let me put a bracket here. This is what we have for B. Is that right? Okay. Oh, except there's a minus sign. Minus. Yes. Okay, let me put a minus sign. Okay. Upstairs. Inside the bracket. So this. Cross. There is the C. Which is not here. So C times R hat cross whatever is here. So cross B. Obviously, B is orthogonal to R, and now E is orthogonal to R as well as the B. Sound familiar? So we have, let's say that we have this is the direction of observation, R hat. Let's call this E direction, then B will be this direction, perpendicular to each other. So let's see. E is given by R cross B will be put up. Oh, there's a sign mistake. R cross B is minus this E cross B. So I made a sign mistake somewhere. I have to check it down. Oh, it's quite painful. Sorry, I'm not very good in doing calculations. So yeah, there is a minus sign. And I don't know where I made a mistake. Along the way, there's a minus sign mistake. So there's minus sign. Exercise. Find my mistake. Find this minus sign. It's there. Somehow, and I don't know where. Yeah, there was a minus sign. Okay. And must have escaped my. There's minus sign. Sorry. There is. There's a minus sign. So it was no mistake at all. There's a minus sign. Final mistake. Okay. And okay. You can also take curve this. Okay. You will find B in terms of E. Into that. So over here, B is related to E by a factor of 1 over C, and B is given by R cross E. And this is E. Okay. So since E is related to B in this fashion, okay, magnitude-wise they're the same. So that E squared is equal to B squared times C squared. They're of the same amplitude. Okay? And so that from now on, in fact, let me concentrate on the B. Once we know B, we know E. So we should obviously keep this. And let's stop at this point and continue the calculation next time.